This is the Masterclass video for the topics of current electricity, DC circuits, and practical electricity. We start with a revision of the common formulas which we'll be using in these three chapters. Formulas which we'll be using in these three chapters. QIT, charge is current times time. Note the SI units of Coulomb for charge, ampere for current, and seconds for time. The EMF or potential difference or voltage is the work done or energy converted per unit charge, VIR. R is rho L over A. For two resistors in a series circuit, the total or the effective resistance of the circuit is the individual resistance of A plus the resistance of B. The current at any point in a series circuit is the same. So the current that comes out from the battery is the same as the current flowing through resistor A, and which is the same as the current flowing through resistor B. The EMF of the battery is the potential difference across A plus the potential difference across B. For two resistors connected in a parallel circuit, you want to find the effective or the total resistance. 1 over the total resistance is 1 over RA plus RB plus 1 over RC. Why is the first denominator RA plus RB? Because the same current of I1 flows through resistor A and B. Therefore, resistor A and B are connected in series. Then solve for the total or the effective resistance REFF. Current splits in a parallel circuit. So the current that comes out from the battery is I1 plus I2. Potential difference across parallel branches of a parallel circuit is the same. Therefore, the EMF of the battery is the potential difference across resistor C. But it is also the same as the potential difference across resistors A and B, VA plus VB. Why is it VA plus VB? Because as mentioned earlier, A and B are connected in series. And in a series circuit, the resistors share the potential difference. For the topic of practical electricity, these are the formulas we should be using for energy and power. There are four formulas each for energy and power. E equals to PT, E equals to VIT, E equals to I square RT, E equals to V square over RT. Any of these four formulas will give you the same energy calculated. E is the energy in joules, V is the voltage in volts, I is the current in ampere, R is the resistance in ohm, while P is the power in watt. The four formulas of power are P equals to E over T, P equals to VI, which a lot of you are very familiar with, P equals to I square R, P equals to V square over R. To calculate the cost of electrical energy used, we use EPT. But take note, if you want to calculate the cost of electricity consumption, please take note that the energy, it should be in kilowatt hour. The power should be in kilowatt and the time should be in hour. First, calculate the total energy used by using E equals to PT. Then, take the total energy in kilowatt hour multiplied by the cost per unit, which is per kilowatt hour, and you get the total cost. Three resistors X, Y, and Z are connected in parallel to a 6-volt battery as shown in the figure. The total effective resistance of the circuit is 0.75 ohms. The current in X is 3 ampere and the current in Y is 1 ampere. With an effective resistance of 0.75 ohms, this means that I can redraw the battery of 6 volt with a single resistor of resistance 0.75 ohms. With this, I can use VIR to find the current that comes out from the battery, which is 8 ampere. In the parallel circuit, current splits. So the current that comes out from the battery 8 ampere is equal to the current in X 3 ampere plus the current in Y 1 ampere plus the current in Z. Therefore, in part 2, if I want to find the current in resistor Z, it is 8 minus 3 minus 1, which gives me 4 ampere, highlighted in green. How do I find the resistance of resistor Z? Earlier on, we learned that the potential difference across parallel branches of a parallel circuit is the same, meaning since the EMF of the battery is 6 volt, the potential difference across the first branch, resistor X, is 6 volts. The potential difference across Y is also 6 volts, and so is the potential difference across Z. Now, to find the resistance of Z, I use VIR. 6 volt divided by 4 ampere flowing through Z, found in part 2, I get 1.5 ohms. Calculate the amount of energy transferred in resistor X in 15 minutes. There are many ways that you can apply to find the answer to this question. This is only one of the many ways. First, you can use power, something you are very familiar with, P equals to VI. 6 volt multiplied by 3 ampere current flowing through X. I get 18 watts as the power of X. Then I use EPT, 18 watts multiplied by 15 minutes times 6T. An important reminder that your time must be in seconds. That will give you the energy transferred as 16,200 joules. A 12-volt battery is connected across a parallel arrangement of 2 resistors. In a parallel circuit, current comes out from the positive terminal and splits. So we can see that the red current splits into the pink and the blue current. We're going to use VIR. The current that flows out from the battery is the same as the ammeter reading which we are finding. Alright, we need to find the current that flows through the 3 ohm resistor as well as the current that flows through the 6 ohm resistor and add them together. We learned that the potential difference across parallel branches of a parallel circuit is the same. So the potential difference across the 6 ohm resistor and the 3 ohm resistor is 12 volts, the same as the EMF of the battery. The ammeter reading is 12 volts divided by 6 ohm, which is the current that is flowing through the 6 ohm resistor, plus 12 volts divided by 3 ohms, which is the blue current, the current flowing through the 3 ohm resistor. 4 plus 2, that will give us the ammeter reading of 6 ampere. D. A wire of length 0.50 meters and a cross-sectional area of 1 times 10 to the power minus 6 meters square has a resistance of 0.75 ohms. Another wire of the same material, therefore, the resistivity of the two wires will be the same. It is the same resistivity, not the same resistance. Resistivity depends on the material of the wire. Same material, same resistivity. The length is 2 meters and the cross-sectional area is 0.50 times 10 to the power minus 6 meters squared. Find the resistance of this second longer wire. We recall that resistance has a direct relationship with length. From 0.50 meters to 2 meters, the length multiplied by 4. Since resistance has a direct relationship with length, length times 4, resistance times 4 as well. So 0.75 ohms times 4 will give us 3 ohms. Resistance has an inverse relationship with cross-sectional area. So when the area changes from 1.0 times 10 to the power minus 6 meters squared to 0.50 times 10 to the power minus 6 meters squared, area divided by 2. Resistance opposite, inverse relationship. Resistance times 2. Taking the resistance we just calculated in the first part earlier of 3 ohms times 2, it will give us 6 ohms. D. A circuit contains a battery, 3 identical ammeters A1, 2, and 3, and 2 resistors of resistances 4000 and 2000 ohms, as shown in figure 7.1. Current comes out from the positive terminal and splits up. So the red current splits up into the blue and the pink. We are told that the reading on ammeter A1 is 2 milliampere. So with that, we need to find the potential difference across the 2000 ohm resistor first. We use V equals IR, 2 milliampere times 2000 ohms. Reminder to change the prefix of milli to 10 to the power minus 3. So 2 times 10 to the power minus 3 ampere times 2000 ohms gives us a potential difference of 4 volts. Potential difference across parallel branches of a parallel circuit is the same. So the potential difference across the 4000 ohm resistor is also 4 volts. The EMF of the battery is also 4 volts. With that, we can find the current flowing through the 4000 ohm resistor using similarly V equals IR. So 4 volts divided by 4,000 ohms give us 0.001 ampere or 1 milliampere. Since current splits in a parallel circuit, A3 will be equals to A1 plus A2. The blue plus the pink is give us the red current. So 2 plus 1 will give us 3 milliampere. Calculate the potential difference across the battery, or the EMF in this case. We have actually done this earlier, which is 4 volts. Calculate the energy transfer in 5 minutes in a 2000 ohm resistor. There are many ways to do this, as mentioned in the previous question. This is one of the ways. We first find the power. P equals to VI, 4 volts times the current of 2 milliampere that flows through the 2000 ohm resistor. So change the prefix milli to times 10 to the power minus 3 ampere. We'll get the power as 0.008 watts. That we then use EPT, energy is power times time. 0.008 watts multiplied by 5 minutes. Remember to change the time to SI unit of seconds, times 60. That will give us 2.4 joules. The input power of a radio is 6 watts. The energy is provided by a rechargeable battery. When the battery needs to be recharged, it is given a charge of 12,000 coulomb by passing a current of 600 milliampere through it. Calculate the time taken for the charge of 12,000 coulombs to be supplied to the battery using a current of 600 milliampere. You are given charge, you are given current. How do I find time? We use QIT. But take note of the SI units. That current should be in ampere. With a prefix of milli there, you need to remember to change the milli to 10 to the power minus 3. So time T is Q divided by I. 12,000 coulomb divided by 600 times 10 to the power minus 3 ampere, which gives us 20,000 seconds. The total input energy to the radio is 72,000 joules. Calculate the time for which the radio will operate. The first sentence of the question tells us that the power is 6 watts. Energy is 72,000 joules. We're going to use the formula of EPT. Time is energy divided by power. 72,000 joules divided by 6 watts gives us 12,000 seconds. Resistors X and Y are connected in parallel to a DC power supply as shown. We are given the VI graphs for both X and Y. Part A says that for an output potential difference of 6 volt from the DC supply, use the graph to determine the current X and Y. So we show the working on the graph itself. Use dotted lines to show your working. From a potential difference of 6 volts, we find the current from the x-axis for both X and Y. So the current in X, represented in red, should be 0.4 ampere. The current in Y, represented by the blue line, gives us 0.5 ampere. Since current splits in a parallel circuit, what is the total current? We add it together. 0.4 plus 0.5 gives us 0.9 ampere. Calculate the energy dissipated in Y only. Take note that Y only is in bold in 10 minutes for the potential difference of 6 volt. Again, there are many ways to calculate energy. If I use power, P equals to VI, 6 volt times 0.5 ampere in Y only, I get 3 watts. EPT, 3 watts times 10 minutes, remember to change the time to SI unit of seconds, times 60 seconds, 1,800 joules. The resistance of X changes with temperature. It is connected in series to a fixed resistor Y of resistance 1 kilo ohms or 1000 ohms and a 12 volt battery. While given in figure 11.2, the variation in temperature of the resistance of X. So as temperature increases, the resistance of X decreases. For the temperature of 30 degrees Celsius, use the graph given to determine the resistance of X. Again, we show our working on the graph given. Use dotted lines. For 30 degrees Celsius, the resistance of X should be 800 ohms. Calculate the current in the circuit. Since this is a series circuit, X and Y are connected in series. Before we can find the current in the circuit, we need to find the total or the effective resistance of the circuit. For a series circuit, we add the two individual resistance together. 800 ohms plus 1000 ohms give us the effective resistance of 1800 ohms. This means that I can redraw the circuit with a single resistor 1800 ohms connected to a 12-volt battery. VIR, I is V over R. 12 volts divided by 1800 ohms give us a current of 0.00667 ampere to 3 SF. Reminder, no fractions in physics. Since this is a series circuit, the same current of 0.00667 ampere flows through the entire circuit. So, to find part 3, calculate the potential difference across resistor Y. The same current of 0.00667 ampere flows through Y as well. We use VIR. I times 1000 ohms, the resistance of Y, gives us 6.67 volts. Part B. The temperature then rises. State and explain what happens to the current in the circuit. Now we can see from the graph in 11.2 that when the temperature increases, the resistance of X actually decreases. Since this is a series circuit, the effective resistance of the circuit decreases when the resistance of X decreases. VIR, the current in the circuit, is equals to the EMF of the battery V over R. When the total resistance of the circuit decreases, the current in the circuit will increase. B part 2. What then happens to the potential difference across resistor Y? The resistance of Y is constant at 1000 ohms. V equals IR. When the larger current flows in the circuit from B part 1, we know that the potential difference across Y should increase as well. Since this is a series circuit, the EMF of the battery, 12 volts, will be the potential difference across X plus the potential difference across Y. Since the potential difference across Y is greater, the potential difference across X is now smaller, since the EMF of the battery is constant. What is the function of a fuse and how does it work? A fuse prevents overheating the circuit. How does the fuse work? When the current in the circuit exceeds the fuse rating, the fuse will melt and break the circuit. Please take note of the words in red that have been struck out. Many of you like to use when the current in the circuit is too high, when there's excessive current in the circuit. But fuse rating changes from one electrical circuit to another. So the fuse rating changes, the maximum current that is allowed in each circuit will also change. So too high is subjective. Please do not use excessive current, too much current, or the current is too high. But when the current exceeds, when it's greater than the fuse rating, there's a red star placed beside this part question because the function of a fuse and how does a fuse work is a very important fundamental question in the topic of practical electricity. Please make sure you learn this part. An electric heater takes a current of 4 ampere from a 250 volt supply. How long does it take to convert 400,000 joules of electrical energy? We use the formula E equals to VIT. Energy is the voltage times current times time. T equals to E over VI. 400,000 joules divided by 250 volts times 4 ampere current. We get 400 seconds. A. The circuit shows the correct positions for the fuse and the switch in the lighting circuit of a house. A very important thing to take note is that the fuse and the switch in the circuit must be connected to the live wire, while the metal casing must be connected to the earth wire. This is a very important thing that you must remember. So you can see a red star there. All those that have a red star beside it for this video, please make sure that you know them. Alright, so the answer for this question is D. The live wire of a 240 volts main supply is protected by a 15 ampere fuse. A 3 kilowatt heater is connected to the supply. The arrangement is as shown in the figure. Name the wires P, Q, R. Recall what we learned in the previous question that the fuse and the switch must be connected to the live wire. Therefore, we can see that in this figure, wire P is the wire that is connected to the fuse and the switch. Therefore, wire P must be the live wire. The earth wire must be connected to the metal casing. The metal casing is in dotted lines on the right side. And we can see that wire R is the wire connected to this metal casing. Therefore, R must be the earth wire. This leaves Q to be the neutral wire. Fully describe the function of the earth wire. Please take note that this is a must-know fundamental question for the topic of practical electricity. So there's going to be a red star beside this question. Make sure you know this. In the event of electrical fault, when the metal casing becomes live at the high mains potential of 230 or 240 volts, the high current will be conducted to earth through the earth wire, which has negligible resistance. The user is protected from possible electrocution shocks. Please take note, even when the earth wire is activated to conduct the current to earth, the fuse will still melt due to the high current in the circuit, and the fuse will break the circuit when it melts. This is a must know. The user wishes to connect another 2 kilowatts heater in parallel with the 3 kilowatts heater. Discuss using suitable calculations whether this is a feasible idea. If this is a parallel circuit, current splits. We need to find the total current in the circuit from both heaters. We're going to use the formula of PVI. So the total current is the power of the 3 kilowatt heater, 3000 watts, divided by 240 volts, plus the power of the 2 kilowatt heater, 2000 watts, divided by 240 volts. Add up the total current and I get 20.8 ampere. This circuit is connected to a 15 ampere fuse. Therefore, this is not a feasible idea, as the total current in the circuit, 20.8 amperes, would exceed the fuse rating of 15 ampere. When that happens, the fuse will melt and break the circuit. The figure shows the wiring inside a 3-pin plug. This is something you've learned before in lower sec, so it's a revision. First, we always name the wire that is connected to the fuse first. We can see that the fuse is the cylindrical component on the right side. So the wire that is connected to the fuse is the live wire, and the live wire is brown in color. The wire at the top is always the earth wire, which is green and yellow stripes. That leaves us the last wire, which is the neutral wire, which is blue in color. Explain why the switch of an appliance must be connected to the live wire rather than the neutral wire. Take note that this is also a very fundamental must-know question for the topic of practical electricity. So there's definitely going to be a red star here. When the switch is off for this question, or if the question changes to why must the fuse be connected to the live wire, you can also use the same explanation but just change the words to when the fuse is blown. So when the switch is off or when the fuse is blown, the appliance would be disconnected from the high mains potential or the high mains voltage. Please take note of this. There's a red star, must know.